Hydrogen peroxide has 2 hydrogens and 2 oxygens. It's basically water with an extra oxygen. It can decompose. It just falls apart and makes oxygen gas, that's a gas, and water. Water, in this case, would be a liquid. Hydrogen peroxide usually is bought as a 3% solution, and that is what we are using in this lab. And so solution means dissolved in water in this case. And so I can put an AQ here, it's aqueous, which just means dissolved in water. Oxygen is a diatomic, di meaning two atoms stuck together. We draw oxygen like this, and again, we'll get back to why that is in more detail later on in the semester. Water is a bent molecule, and it's drawn like this. We just get comfortable drawing them like that. We notice a challenge right off, meaning that this is not a balanced reaction. If we look over here, we have 2 oxygens, and over here we have 3 oxygens. There are 2 hydrogens and 2 hydrogens. Basically what's happening here is a hydrogen peroxide is losing 1 oxygen, but it has to make diatomic oxygen. So we're going to need 2 of these and end up with 2 of these. The reason is that these oxygens are going to come together, leave behind some waters to make that, and that's a balanced reaction. So to balance this, we put a 2 there and a 2 there. I'm confident if you're a little patient with that, you can come to understand that. When hydrogen peroxide decomposes, it also makes heat. And the truth is that hydrogen peroxide doesn't just decompose. If you buy hydrogen peroxide, it will stay hydrogen peroxide unless it's put in the presence of a catalyst. In this case, in this class, we're going to use manganese dioxide as the catalyst, and the catalyst goes over the arrow, over the top of the reaction arrow, because it's not used in the reaction. It's there. The reaction does not happen unless the catalyst is present. That's the definition of the catalyst, but the catalyst is not used up in the reaction. You don't see it on the reactants or product side. To truly understand this reaction, we need to look at the potential energy surface. Here we have the reactants and the products. We know the reactants are higher in energy than the products because this reaction produces heat. And we talked about that analogy. If something starts with a lot of energy and then loses the energy, it goes downhill. The energy has to go somewhere. This is the analogy we made, is if there was a rock at the top of a mountain, it would have a lot of potential energy. And if that rock fell to the bottom of the mountain, when it got there, it would lose its potential energy, but energy cannot be created or destroyed, so that energy has to go somewhere. In fact, in that case, the energy would also go to heat. It would make some sound, the sound would dissipate, the sound would go to heat as well. Here the reactants are the 2 molecules of hydrogen peroxide in the aqueous form, and the products are oxygen gas and 2 molecules of water. The energy lost is the heat produced in the reaction. And in fact, you see that delta there and that delta there are the same. The deal is that this reaction doesn't just happen. There is an energy barrier to this reaction happening, and it's like a rock rolling down a mountain. It won't roll down a mountain if it has to roll up a hill to roll down the mountain. And this reaction doesn't go. We know that. You can buy hydrogen peroxide in the store. It can sit on a shelf for a long time. It doesn't just start making bubbles for no reason. And because that doesn't happen, then I know there's a barrier to the reaction happening. And this is called the activation energy barrier. It's written as a capital E with a little subscript A, and that's the activation energy barrier. In fact, this reaction will go if you put it in sunlight, because the sunlight can give it energy to go over the reaction. So you can see that if you put hydrogen peroxide out in sunlight, it will start bubbling. Another way to make this reaction go is to put it in the presence of a catalyst. And if you do that, what the catalyst does is it destroys the barrier. The catalyst makes a direct path. So here, this line is with the catalyst present. And what the catalyst does is it destroys, that's not spelled right, but whatever, destroys the activation energy barrier. It also orients things, it does some other things, but the big point I want you to get across is the potential energy surface, what's required for the reaction to happen, actually changes when the catalyst is present. Remember this vertical axis here, this is chemical energy, and the horizontal axis here is reaction progress. So going this way across, reaction progress shows that reactants are becoming products, and the energy required for that to happen, if there is no catalyst present, then energy has to be put into the system to get over the activation energy barrier and create products. In this case, that energy can be sunlight, or a catalyst can be put into the solution which destroys the barrier, which we saw in class. And if we put the catalyst in, the reaction just goes as we would expect a rock to roll downhill if nothing were in its way. I will add one additional thing that catalysts do. They don't always just lower the activation energy barrier. Sometimes they hold things in place. Like, for example, this hydrogen peroxide molecule cannot just fall apart by losing an oxygen. That oxygen has to have somewhere to go, so it needs two oxygens. So what has to happen for this to fall apart is two hydrogen peroxide molecules have to come together, like you see here. And then this hydrogen has to jump over to that oxygen, and this hydrogen has to jump over to that oxygen. And in molecular terms, that's a lot. And so what happens here is the catalyst kind of holds things in place and orients the molecules so that all that can happen. And then this O2 jumps out. I'm going to draw this line down through here to show that this side is the reactants and that side's going to be the products. And so this, what's in this circle is two oxygens, and those two oxygens can jump out of there. And then after what that happens, what's left over is this, which is a water. And you see there's another one here. There's another water molecule right there. And so those two come over here as well as products and make two water molecules. And again, while we're at it, we'll notice that if we look at this drawing, hydrogen always has one bond. One bond there. Here, hydrogen has one bond, one bond. Oxygens always have two bonds. You can see here there's a bond there and a bond there. And this oxygen would have a bond there and a bond there. Each of these oxygens each have two bonds. And oxygens always have two lone pairs of electrons. Again, there's reasons for these things, and we'll get to it later in the semester. But here you can see this oxygen has two bonds, and this oxygen also has two lone pairs. So the catalyst lowers the activation energy barrier. In this case, it can hold and orient the molecules so that there's time for all this atomic reorganization to happen.